Welcome to the Introduction to the WRF Modeling System talk. We will provide some introductory remarks about the modeling system you are about to learn. In case you are new to numerical modeling, there are some basic concepts we will discuss in this talk that may be helpful to you. These are the topics we are going to cover in this talk. We are going to talk a bit about WRF history and show some typical WRF applications. Since the WRF model is mostly used as a regional numerical weather prediction model, we will briefly discuss some basic concepts about modeling and modeling in limited areas. We will then introduce the WRF modeling system and show you what it looks like to you and what you can expect when working with it. We will talk about what are covered in this tutorial and what you should expect to learn from it. So what is WRF? WRF stands for Weather, Research and Forecasting Model. Often, when we speak of WRF, we also refer to the system, which includes the programs that supports the model itself. The model was originally developed by NCAR and NOAA with funding from a number of federal agencies and supported to the community as free and shared resources. NCAR developed one of the dynamical cores, the software framework, and ported a number of physics to WRF from an old mesoscale model called MMM5. The majority of physics options in the model now are contributed from researchers everywhere around the world. We recently moved user support to a public forum, and hence everyone from the community can participate too. The WRF model is 20 years old from its first public release in December of 2000. Since version 3 in 2008, we have released a major version each year, the first and second digit in the release number, and minor ones within each year. Each major release usually has several new developments, typically new physics or other new capabilities, such as climate diagnostics. The most recent generation is number 4, which made the hybrid vertical coordinate the default of the model. The last major release is version 4.2 from last April. Since version 4.0, the model is released on GitHub. Here's a screenshot of 4.2.1 release from GitHub. As of the end of December 2020, we have WRF model users from 184 countries and nations, with a total number of users over 52,500. US has the largest number of users at about 26% of the total. The number of new users has leveled to at about 4,000 each year in the last 5 to 6 years, as shown on this simple plot. And most of our users have university connections. The WRF model has 2 dynamical cores. One is called the Advanced Research WRF, or ARW, and the other one, NMM, non-hydrostatic mesoscale model. A dynamical core of the model usually refers to how a model solves the governing equations numerically and how it does time integration, and so on. The WRF-AirW is developed by the mesoscale and macroscale meteorology laboratory at NCAR, while WRF-MMM at NCEP, the National Centers for Environmental Prediction. However, NCEP has recently moved to a new model, and there's no further development of MMM. This tutorial is for AirW only, and when we talk about WRF-AirW, we often drop AirW for simplicity. WRF is not designed for a single purpose. Its design embraces generality, flexibility, and the easiness to use, and adaptable for other extensions. That is one of the reasons WRF is used in many disciplines, sometimes beyond atmospheric sciences. But first of all, WRF is a research tool. The model can be used to study atmospheric phenomena using idealized initial conditions. This picture depicts a three-dimensional simulation of supercell thunderstorm. The model can be used for experimental real-time forecast. This picture shows precipitation types from an ensemble forecast. The model is often used to simulate continental convection, as shown by this picture, which depicts the simulated radar reflectivity compared to the actual reflectivity composite. Or a hurricane making landfall, as shown by this plot of simulated surface wind. The model is also used to develop ensemble forecast products, like this one showing here for column reflectivity greater than 40 dBz from members of an explicit convection prediction ensemble. The model is also popular for regional climate research, data simulation development, and the chemistry simulations. In summary, the model can be used for developing and testing physical parameterizations, studying atmospheric flows, special weather events, regional climate, research using coupled chemistry, hydrology, and fire modules, and the data assimilation. The model has been used as a teaching tool for numerical weather prediction classes. In many organizations, the model is used for forecasting local weather, for wind and solar energy prediction, and for air quality forecast, both online and offline. We know a numerical model like WRF can be a great tool to assist us to explore many science issues. But how does a numerical model work? A numerical model starts with an atmospheric state and advances in time to look for a solution at some future time based on the governing equation of the model and the physics employed. In concept, one can think about a model in this simple differential equation form. Here, A is a variable we would like to find future solution for. T is time. F is forcing. As expressed by this equation, the change of variable A with time will depend on the forcing term, F, which in our model represents all of the atmospheric processes, both dynamical and physical. Hence, the solution of A at some future time can be written as the value of A at the start time, i.e. the initial condition, plus the forcing in the model times the time step, delta t. Because the forcing term varies with time, one cannot get the solution of A in the future in one time step. So in the model, the solution is obtained in many time steps, which we call time integration, as shown in this next equation. You will hear we talk a lot about model initial conditions and the time integration in this tutorial. Now we have some idea on how a numerical model gets its solution. We may ask how the atmospheric data is represented in the model. Here on the left, the red contours shows temperature one could draw on a surface map, which looks smooth and continuous. In the numerical model, the data is represented only one value per grid cell, as shown on the right here, a process called discretization. And the model equations are solved on these discretized grid cells. The value in the grid cell can be interpreted as representative values of averages of the grid cell. Now we're going to talk about limited area model. That is what WRF is. This picture shows a map of the world. For a global model, the model needs an initial state to start, and that's all it needs. For a limited area model or a regional model, however, it is quite obvious that that is not enough. In addition to the initial state of the atmosphere inside the limited area domain, we need something to let us know what happens outside the limited area. This is where the concept of lateral boundary condition comes in. For a limited area model, it needs data from a global model to define the flow condition outside the regional model. The global data comes into the regional model as data at the lateral boundaries, as it is illustrated by the blue dots on this figure, which we call the lateral boundary condition. This figure is just a three-dimensional illustration of a limited area model. It is also clear that we need the data at the lateral boundary, not just for the model initial time, but for the entire simulation period. In addition, we also need to think about the lower boundary of the model. Over land, we need to know what happens below the lowest soil layers. Over water, we often need to prescribe the sea surface temperature or sea ice if we don't have an ocean model or sea ice model. Within the limited area model, one can add another domain with high resolution, a method referred to as nesting. One can think of nesting in limited area model in some similar way to a LAM in a global model. The difference is that a nest domain in LAM is run together with its parent domain, and therefore its boundary values are provided by the parent domain at every parent domain time step. The nesting process can be repeated for multiple domains with progressively higher resolution, as shown in this picture here, which has a total of 4 domains and 3 nested domains. Why do we do nesting? Nesting, if done right, is an efficient way to produce model solution at a higher resolution in a localized area. Over the higher resolution region, the model can represent the forcing from the surface better, such as from higher resolution topography and land use. The top plot here shows the topography represented by the model at 30 kilometer resolution, and the bottom is the land use. As you may recognize, this domain covers the Europe and the Alps. When the grid size decreases to 10 kilometers, we can see that the representation of the topography and the land use improve. Going down further to 1 kilometer grid size, the features are represented even better. Now you can see the valleys in the Alps, and the coastlines are sharper. At higher model resolution, the atmospheric flow features can also be resolved better by the dynamics of the model. You may ask, if the solution from higher resolution models are better, why don't we all run models at a higher resolution? One of the important reasons is that higher resolution models cost a lot more to run. Covering the same area and maintaining the same number of vertical levels, roughly a 10-kilometer model would cost about 27 times more than a 30-kilometer model. And the 1-kilometer model would cost 1,000 times more than the 10-kilometer model. Sometimes it may be helpful to see our limited area domain in a three-dimensional view. Here, the box represents our limited area domain. It shows model horizontal grid at the bottom, the terrain following vertical coordinate as shown by the light blue surfaces, and the forcing from global models on the lateral boundaries of the box. It also reminded us that there are some processes the model can represent or resolve, like the stratiform cloud feature on the left side of the box. And there are processes the model cannot resolve, such as the convective cloud showing on the right side of the box. For the process the model cannot represent explicitly or resolve, we parameterize them or filter them out. The black box in the middle is just an illustration of a nested domain. Now, what is it like to work with the WRF model? First, the modeling system programs are not GUI-driven. We work on Unix terminals and use Unix commands to operate the model. So we are going to learn how to type and make plenty of mistakes along the way. We also use simple graphic tools to view and examine the data created by various modeling system programs. The modeling system have many functionalities. There are many different ways to run a model. Decisions are needed at every step, such as what input data to use, how do we configure a domain, and what model options are better for my applications. And best practices are required. Now we're going to introduce the WRF modeling system software. This flowchart shows the programs and data flow of the model system. We have the WRF model, the WRF pre-processing programs, post-processing of visualization programs, and the data required for various programs to use in the system. We are going to cover these programs in great details. These are WRF model itself, but not chemistry and fire. The WRF pre-processing system, one post-processing tool, NCL. We will talk about the data required for the model to run, both terrestrial and meteorological. We will briefly discuss programs OpsGrid, which is a program for doing objective analysis, and the RIB4 for computing diagnostics and plotting. Here is a closer look at the WRF pre-processing system and the WRF programs. Program GeoGrid is the program we use to design our simulation domain. And we use it to interpolate terrestrial data onto the model domain. The data processed in GeoGrid is typically used in the model as time invariant field. For example, topography and land use. Program OnGrid decodes and reformats meteorological data from another model. And the data processed here typically varies with time. For example, atmospheric temperature and winds comes from this program. Program MatGrid takes the domain information from GeoGrid and the data from OnGrid and interpolate it onto the model domain. This interpolation is only horizontal. Once the data is processed by WPS, they can be used by program REAL, which defines the model vertical grid and interpolates data to that vertical grid. The data from REAL is the input to the WRF model. This is a typical data flow for a real data application of the model. The model can also be run with idealized initial state, and this is done via program ideal.exe. So what we're going to learn in this tutorial, we're going to learn to set up the simulation domains. We're going to learn how to process data and prepare initial and lateral boundary conditions for the model. We will learn how to run pre-processing programs as well as the model. We are going to learn how the model works. This includes how the model is formulated and how we solve model equation numerically. We're going to learn the physics in the model and what processes in the atmosphere are represented. We're also going to learn something about model software and how we can run the model efficiently using large computers. We're going to cover some post-processing tools for viewing and analyzing model data. We will also learn the basics to install the modeling system code, as well as best practices when using the model and what to consider when verifying model output. In summary, it is our goal to provide you with enough information to get started on basic model applications, to have some basic understanding how the model works, and gain familiarity with the process to run the model. But consider this tutorial only as a starting point. There's still a lot to learn about this modeling system. The best advice we can provide is to read more and experiment, and practice, practice, and practice. Here are some books that you may find helpful to learn more about numerical modeling and how to apply it in our research. We are now reaching the end of this introduction talk. Thank you for listening and good luck with the rest of the tutorial.